Welcome to a lesson with Dr. Powell. Let's take a look at some motivation for the technique we're going to use to find the maximum value of a function. Has three inputs. The maximum value of this function subject to a constraint. Perhaps the constraint is that we're taking input values along a curve in space. So imagine the curve is coming up like this. Now what I have illustrated here is a level surface of this function. Now what is a level surface? A level surface is like all the input values that just output one value of this function. So imagine having a formula in three variables and setting that equal to a number. Wouldn't you get a surface out of that? Yes. And it's that idea. The output is equal to a number, and that's like saying a number is equal to an expression in three variables. So we have this level surface. So imagine this level surface is a specific value, and level surfaces below this, like this, maybe represent smaller output values, and level surfaces above represent larger output values. Then it would make sense that if we want to find a point on this curve that maximizes this function, then the curve itself would come up and just tangentially hit this surface in one point and then go back down. That's the same thing as saying that a tangent vector to this curve at the point of intersection is going to be orthogonal to the gradient, because the gradient is orthogonal to the surface, the level surface itself. So we want this tangent vector of the curve to be orthogonal to the gradient. Now, another way of saying that is, well, what if this curve itself was determined by the intersection of two surfaces? Suppose we have two surfaces, maybe two different, which could be thought of as level surfaces of two different functions, perhaps. Maybe g, x, y, z, maybe g1, say, and g2, x, y, z. So you have two different surfaces, and two different surfaces, and so let's just kind of get a little illustration where they come together. What do you notice when they come together? You get a curve. So now, what if all we're given is not an equation of this curve, but what if what we're given instead is equations for the two surfaces, and we know what the output value is for the particular level surface that they determine. So a surface is meaning a level surface of this function, where we're just getting one number output for each. So a number and another number. Okay. So, well, we think for a minute. All right, this curve is inside both surfaces right there, which means that the tangent vector itself along that curve at a particular point is going to be tangent to that surface. And so in particular, so the vector that's tangent right here, just kind of drawing it right here, it's going to be it's going to be orthogonal to a vector that's orthogonal to that surface right there. So in other words, maybe if this surface is g1, maybe, or a level surface of g1, then we take the gradient g1. It's going to be orthogonal to that, but similarly, it's also going to be orthogonal to the gradient g2. So that means that these two gradient vectors make up the plane of all vectors that are orthogonal to this tangent vector. So if we want this gradient to be orthogonal to that tangent vector, then it better live in the same plane that these two guys live in. So another way of saying that is just this, is equal to some constant, which we use a letter lambda here, Greek letter lambda, some constant scalar of this gradient plus some constant scalar. This is a Greek mu of the other gradient. So if we have this happening at all, that really guarantees that this guy right here is going to be orthogonal to the tangent to the curve of the two constraints, and that thus maximize this function on that curve. So basically all we need to do is be able to find points x, y, z such that we have this happening. Now, just a little note, when we do that, we actually have 5 equations when we do that, because we have G1 and G2, they're level surface equations. We need both of them satisfied for the intersection. And then, since we have 3 components here, we have 3 equations. This equation is really 3 equations because 1 in each component. So you have 3 and 2, that's 5 total equations, and you have 5 unknowns because you have x, y, z, and lambda and mu. So solving a system of a 5 by 5 system will actually help us to be able to find specific points where this function right here is maximized on that curve. Thanks for watching.